Hello students, today's our topic is different type of quantum numbers which can easily describe the vector atomic model and the presence of different electrons in different orbits. The first type of quantum number is the principal quantum number, which we already studied in the Bohr atomic model. It is denoted by small n and it gives the distance of the electron from the nucleus. As n is the principal quantum number having values 1, 2, 3 up to so on. As the number of the principal quantum number goes on increasing, the distance of the electron from the nucleus goes on increasing. For principal quantum number n is equal to 1, this electronic shell is represented by K shell, you know very well, and when n is equal to 2, it is our energy level L, and when n is equal to 3, it is our energy level M. Hence, we show that these principal quantum numbers gives the distance of electron from the nucleus. It means it can give us the size of our atom. It can define the size of our atom. Second, they also define the energy of the given electron in a particular particular principal quantum number. Third is, if we know the principal quantum number, we can easily define the binding energy of the electron present in different shells with different principal quantum number. These are the three characteristics of the principal quantum number which define the distance of electron from the nucleus, energy of the electron, and binding energy of the electron. Second quantum number is known as orbital quantum number. Orbital quantum number defines the motion in orbit of an electron. We know very well, according to vector atomic model, the electron moves in an elliptical path and nucleus is situated at one of the focus. In orbital quantum number, the symbol is given by L and the values of orbital quantum number start from 0, 1, 2 up to so on, where L is equal to 0 defines the S subshells and P is equal to 1 defines the P subshell. To L is equal to 2 define the D subshells. Orbital quantum number has a relation with azimuthal quantum number, that is K, and we know that azimuthal quantum number is never equal to 0. Then what is the relation between azimuthal quantum number and orbital quantum number? L is equal to K minus 1. This is the relation in between the orbital quantum number and the azimuthal quantum number. Let us consider for n is equal to 1, we have to find the orbital quantum number. Orbital quantum number and principal quantum number is given by this relation. L is equal to n minus 1 up to this tends to 0. It means when n is equal to 1, L comes out to be having a value L is equal to 0. When n is equal to 2, the value of L is equal to n minus 1, that is 1 up to 0. Similarly, when n is equal to 3, we will have the value of L is equal to n minus 1, that is 2, up to 0, including all the integers, and now the integer left here is 1. It means value of L depends upon the value of n. If n is equal to 3, there are 3 possible values of L. When n is equal to 2, there are 2 possible values of L. Where L is equal to 2, define the D subshell, and L is equal to 1, define the P subshell, and L is equal to 0, define the LS subshell. The quantum number L is very important to us because it gives the orbital angular momentum of our electron. We know that angular momentum defines the angular motion of the electron. This electron is moving in this orbit, and the study of motion is known as orbital angular momentum. According to classical mechanics, the orbital momentum of electron is given by the orbital quantum number times of h cross, where L may be 2, 1, 0, it depends which case you are considering. In quantum mechanics, the orbital quantum number, here we are again denoting it with PL, is given by L star h cross, where L star is obtained with the help of orbital quantum number, and it is given by L into L plus 1 whole under the root. It means when L is equal to 2, we can define the angular motion of this electron which is present here, and the angular momentum of electron is given by L star h cross, where in case of L is equal to 2, it becomes 2 into 3, that is under root 6 times of h cross. You can easily find out the angular momentum if you know the value of orbital quantum number. Orbital quantum number defines the binding of electron with nucleus. As the orbital quantum number goes on increasing, the binding of electron with nucleus goes on decreasing. For example, when L is equal to 0, it means the value of L is small. The subshell or the suborbit is denoted by S, and the electron which is in S is strongly bounded with nucleus. When the value of L goes on increasing, now in this case, when L is equal to 1, we here get the suborbit in the electron which are moving in the suborbit P, and we know that electrons in P is less bounded as compared to the electrons in S. It means as the quantum number, orbital quantum number goes on increasing, the binding of the electrons in the different subshells goes on decreasing with respect to the nucleus. This is the importance of orbital quantum number. It gives the binding energy of nucleus with electrons, and it also gives, the second importance is that it also gives the orbital angular momentum, that is, we can easily study the orbital motion of the electron if we very well know about the orbital quantum number. The third one is the spin quantum number. Electron have two motions. One is orbital motion and another is circular motion. According to vector atomic model, the electrons move in orbital path as well as orbital moves about its own axis. It means it is spinning. This spin motion is defined with the help of spin quantum number. There are only two values of spin quantum number. If the electron is moving clockwise, then the spin quantum number, which is denoted by S, is given by half. And if the electron is moving anti-clockwise, which we are showing here, the spin quantum number is given by -1/2. Similar to orbital quantum number, we can discuss the motion of our spinning of electron. If we know the spin quantum number, we can easily find out the momentum related to spin. We can easily define the spin motion of the electron. In classical mechanics or in old mechanics, the spin momentum is given by SH cross, and in quantum mechanics it is represented by PS again, and now it is given by S star H cross, where S star is a numeral and it is given by under root of S times of S plus 1. What is the significance to find out the spin momentum? If we are finding that the electron is spinning like that, it means the direction of PS is like that. And if we are showing the orbital motion of electron like that, it means the PL, that is the orbital angular momentum, the direction of the orbital momentum is given like that. The direction of orbital momentum and spin momentum is given with the help of right hand thumb rule. The thumb indicates the direction of the momentas, both orbital and spin, and the curl of the fingers gives the direction the electron is moving in clockwise direction or electron is moving in anti-clockwise direction. In both the cases, whether it is orbital motion or spin motion, we know that a charge is completing the loop. If a charge is completing the loop, this motion produces a magnet. It produces a magnetic effect. Similarly, the spin motion also produces a magnetic effect, and due to the different motions and producing different magnetic fields, we have two more quantum numbers, and these quantum numbers are magnetic quantum numbers. Now, with the help of orbital quantum number and spin quantum number, we will get a total quantum number, which is the vector addition of both these quantum numbers, that is L and S. If L is our orbital quantum number and S is our spin quantum number, then with the help of J, we can indicate the total quantum number, and J moves from L plus S to L minus S, considering all the integers lying in between L plus S and L minus S. Also, if this is a quantum number and it is dealing with the orbital quantum number and spin quantum number, it also gives us total magnetic momentum, and total magnetic momentum in our case is represented by Pj, and it is equal to Jh cross in case of classical mechanics, and it is represented by J star H cross in quantum mechanics. Mainly we consider J star H cross because the value when J star is taken in J into J plus 1 whole under the root, the resultant or the result comes out to be very accurate as compared to the classical mechanics. Hence, in our mathematical problems or in our numerical problems, we consider the quantum mechanical formula for the spin angular momentum as well as for the orbital angular momentum. Hence, there are This is the fourth quantum number. Now, due to the orbital motion and due to the spin motion, we are getting magnetic effects also, and corresponding to this, there is a orbital magnetic momentum. The orbital magnetic momentum, it is the magnetic momentum produced due to this motion of the electron about the nucleus. As we know that this orbital motion of the electron is explained with the help of L, that is orbital quantum number, and due to this motion a magnetic field is produced, and the changing magnetic field is studied with the help of orbital magnetic momentum. This quantum number will define our orbital magnetic momentum. It means orbital motion is defined by orbital quantum number. Orbital magnetic momentum is also defined with the help of orbital quantum number. Let us consider the electron is moving in this orbit for which L is equal to 2. And it means the electron is moving the suborbit D. If L is equal to 2 and electron is moving in this path according to right hand thumb rule, if it is moving in anti-clockwise direction, we will curl our fingers in anti-clockwise direction and we will raise our thumb perpendicular to this curl. We are viewing that the thumb is indicating in the outward direction. It means the direction of our orbital angular momentum is this. It means this is the direction of PL. Maybe this orbit is not lying on paper. Maybe it is like that. It is moving outside the paper. It means now for this motion of the electron in an orbit, now this will be our direction of PL. Direction of PL depends in which orientation electron is moving. Now, to find out orbital magnetic momentum, we will apply a magnetic field about the perpendicular direction of the atom, and let us consider this is the applied magnetic field, and it is denoted by H, and this is the direction of our PL, that is our orbital angular momentum, and it is making an angle of theta. We know that PL depends upon the value of L. It means L will define the direction of PL. The projection of this PL on this magnetic field is indicated by ML, and this ML is known as orbital magnetic quantum number. This is our orbital magnetic quantum number, and it is indicated with the help of ML. The projection of this angular momentum on the applied magnetic field, that this vector, this value is our orbital magnetic momentum, and it has a relation with L, and it is given by L cos theta. For for a particular value of L, ML has different values. It varies from plus L to minus L, including 0 if L is a whole number. If it is an half integral, then the 0 is excluded in this case. We will take an example of the orbital magnetic quantum number in our case. Let us consider the electron is moving in a orbit having orbital quantum number L is equal to 2. According to the relation the ml, that is orbital magnetic quantum number, will be have different values from plus L to minus L, including all the integers, including 0. It means we have to move from plus 2 to plus 1, then we will get 0, and then minus 1 to minus 2. Now, considering H is the applied magnetic field, and this is our direction of PL, making an angle theta. Again, we know that this projection is our ML. This is our ML. We will represent all these 5 values of L in this diagram very easily. Again, consider this is our applied magnetic field, and this is the point where ML is equal to 0. ML is equal to 0 only when L is equal to 0. When L is equal to 0, ML is equal to 0, because we have to move the value of ML from plus L to minus L. It means it is the value where ML is equal to 0. It means we are discussing this. Second, we will start from the first value of L. When L is equal to plus 2, what will be the, when L is equal to 2, ML is equal to plus 2, then what is the angle in between PL and ML? We very well know the relation ML is equal to L cos theta, and in our case ML is equal to 2, L is equal to 2. It means cos theta comes out to be 1. It means the angle is equal to 0. For ML is equal to 2, we have angle L is equal to 0. If it means the angle between ML and H is equal to 0, we will get this vector quantity. For L is equal to 2 and ML is equal to 1, we know that now cos theta comes out to be 1 by 2, and you very well know that this angle is nothing, it is 60 degree of angle. Then if this is our 0 degree, then this is our 60 degree. For L is equal to 1, we will make an angle of 60 degree. Similarly, for L is equal to 0, ML is equal to 0, it means theta comes out to be is 90 degree, because cos theta in this case is equal to 0. We will get this direction. Similarly, for ML is equal to minus 1, we will have 120 degree, and for ML is equal to minus 1, minus 2, we will have the angle of 180 degree. In each case, the magnitude of L is the same, so we are taking the same length of each vector quantity, and we will obtain the value like that. When L is equal to 2, these are the orientations, possible orientations of L across the magnetic field H. It means this is, for L is equal to 2, the electron is not moving in a single orbit, it can move in 5 possible orbits, and these 5 possible orbits are obtained with the value of ML. ML gives the different possible orientations of the orbits in which the electron is moving, corresponding to the orbital quantum number. Similarly, due to the spin motion, as the electron is moving, a charged particle is moving in giving spin, it is also producing a magnetic effect, and due to this magnetic effect,